Esan, maybe you can let people in while we are doing the introduction. So today we are starting the webinar with the next generation of brake discs, the journey of changing material. And we have nice guests with us. You see them, Lucia and Samuel. And also we have a lot of you. We have 56 people signing up for the webinar. We are very happy for that, of course. And actually we have 13 countries represented. So we are really happy to see you all here. And we also would like to see how you find out about, or how you found out about this these webinars. So Esan will give you a short poll. Please help us and answer this short survey before we start. It seems to be LinkedIn and Weblearn newsletter, mostly Weblearn newsletter. I think we can say that we have now, I think it's 400 who signed up for the newsletter. So good. It seems to be working. Good. So you, Esan, decides when you're
yes,
happy with.
We finished the poll, yes.
Yeah. Good. Thank you very much for answering. So let's move on. We are the moderators, Esan and me, Madeleine, and that's about all we have to say about us. As you know, this has been a project, the Weblearn project, but now it has ended, and we have had 1,265 participants over these 2 years, and we have had 55 countries represented, and we are so happy for that. And we have also had a lot of effects about with this. We have new project proposals for research, one new publication, thesis projects, and so on. So this has turned out to be a really good platform for collaboration and networking, among other things. So thank you very much. And we, of course, hope that you will join us for our future adventures, because we will continue, maybe not as often as before, but we will continue. So please join us. Moving on, as usual, we have this webinar format. We hope you can keep your microphones turned off, and we of course want you to engage as much as possible in the chat during the webinar and also in the panel discussion afterwards. We will also give you the webinar recordings after, but not the discussion part. So that's how it works. And I'm sure everyone knows this by now, but you can mute your microphone or unmute here and start your video and the chat function you have here. So that's how it works. And the most important today is, of course, our presenters. So we have with us today Samuel Ave from Automotive Components Floby AB, and also Lucia Latanzi from the Department of Materials and Manufacturing. You will soon hear from them. Just short, we have a short introduction and then we have the presentations. And for the last half hour, we have the time for panel discussion. So please engage in that. Okay, that's the introduction. And now I will stop sharing and let Samuel on stage, please.
Thank you, Madeleine, for the short introduction. My name is Samuel Awe. I work as a research manager at Automotive Component Lubing. And today, the topic we are discussing is on the next generation of brake disc, the journey of changing material. Here is the agenda of this webinar. I will give a brief introduction, information about the AC Flubi. Then for some who are not familiar with the topic, so I'll talk briefly on automotive brake disc and the material requirements for automotive brake disc, and the changing the brake disc material, the possible challenges to overcome, and the required steps for material change. I will also talk briefly on the major trends in the automotive industry in recent years. And the next will be a case study regarding Sika light disc, possible next generation brake disc. Here, Automotive Component Flubi as a company that have been that was founded in 1965, and the company since then have been producing different automotive parts for auto manufacturer. And you could see from the picture some of the products we produce. Here is a brake disc from gray cast iron material. Also, we have brake disc from aluminum composite material, trade name Sika Light brake disc. Then we produce a connecting rod for different vehicle models. We produce wheel hub for trucks, and different processing method and surface treatment we perform at the company. Yes, before we go into the full discussion, we want you to answer this question on the chat. How many of you want to be confident in driving your car? How many of you want to be confident in driving your car? So this is a good question that will give us an introduction to what we are going to discuss. Because brake disc is a safety component which is very, very necessary for the safety of a car. And from here, automotive brake disc is an efficient and effective braking system. That is part of braking system to give safeguard the driving of your vehicle on the road. And this brake rotor that we are talking about today is part of the automotive brake system that ensure that safety when you apply your brake, when you march on your pedal of your vehicle, then the vehicle must stop to prevent accident or collision with other vehicle in case of emergency or any other scenario. So that is the reason why brake disc is a very important component of car safety. And as a result of that, it is well controlled by the stakeholder. The stakeholder, I mean here, the government and the auto part manufacturer. And friction brake disc or decelerate or stop moving vehicles by converting the vehicle's kinetic energy to heat. And this heat is dissipated to the surrounding. So you could see here, you can see that is the brake disc we are talking about. And traditionally, these brake discs have been produced from gray cast iron material from ages. So because of the inherent property of a gray cast iron, which I will discuss later on. And changing this brake disc material will require several considerations, to be put in place before it can be acceptable by the stakeholders and the general public. And during braking regime, so heat is generated, and this heat is majorly concentrated on the subsurface of the disc. And if this heat is continue accumulating during the braking regime, what happens is that it could lead to overheating of the brake component. And this overheating occur that could cause brake fading. Brake fading simply means loss of a friction, and increase in the temperature of the disc lead to increased wear, and that will also lead to thermal cracking as a result of a thermal gradient happening on the surface of the disc. An example of thermal cracking is what you see on the disc here. That is an example of thermal cracking, and which eventually lead to failure of the disc. So as a result of this, it is very, very important to that material for brake disc should meet certain material properties to prevent loss of function. Here are some brake disc material requirements. As I've explained in the introduction, the brake disc material must maintain high temperature property, because the disc is usually subjected to high temperature during braking system and regime. So this material must meet this high temperature property. Then at least it should have a good wear resistance, because we don't want to generate more fine particles. So it should have a good wear resistance. Then it should be corrosion resistant. So now that we have electric vehicle, corrosion becomes so important. So it should be the material should have high corrosion resistance. At the same time, the material should be lighter in weight, especially for the electric vehicle. The weight of electric vehicle is higher, and this is important to. I mean, the OEM are looking different way to reduce the weight, because increase in weight has an effect on the car performance as well, and drive range, especially for electric vehicle. Then there should be excellent heat resistance. Heat transfer capabilities. The material should have a good heat transfer capability. As I've explained in the introduction, during braking regime, you will have a high temperature concentrated on the surface of the disc, and that's the material for brake disc should be able to conduct the heat away from the surface. If not, it will lead to thermal cracking and thermal fatigue failure. Then the brake disc material should have good damping property, or possibly low noise. So this is very important, because material with a poor damping property will create a noise which is uncomfortable, when driving your car. And the material should have an acceptable cost to versus performance, because if you have very material with expensive cost, then it might be that nobody will want to buy it or go for it. So this is some of the material requirements when for brake disc application. Now, changing brake disc material. What are some of the challenges, possible challenges? So beside meeting the material requirements, as I've highlighted earlier, the developed rotors must overcome some of the conditions before it could be accepted. And one of those conditions is that the rotor from the new material must satisfy the minimum safety standard and performance requirement. As I've said earlier on, brake rotor is a part of a safety component of a vehicle. And in that sense, it is well regulated by the government in many countries and the other stakeholders. So therefore, any new material for brake rotor must fulfill or certify these minimum standard safety requirements and performance requirements. Then the rotor must also fulfill several standard brake test procedure. This is performed on the rig testing or bench testing, or usually called dynamometer testing. So after that, the rotor must also pass vehicle brake test procedure. So there is difference between a bench testing testing procedure and the vehicle procedure, because in the dynamometer test procedure, you could simulate in a well-controlled environment, but which is actually different from the real case when driving a car. Because in driving a car, you come with an external environment. Like during winter, you come, the disc come in contact with a cold winter, snow, and also during the winter you have a salt, to de-ice the road. So the disc come across that, and that will create different performance issue. Apart from that, then we also need to look into the dynamic of the vehicle. Aerodynamic of the vehicle play an important role in the performance of the brake rotor. So these are different testing procedure. So the disc must pass vehicle test, and also development of a compatible pad, brake pad, is also important. So which is another concern or another challenge, because if you are developing brake rotor, then you must have a compatible pad for it. You cannot use one particular pad on different materials. So this has to be done, and this has to be done together with a pad manufacturer. So which is another challenge to overcome. After that, manufacturability, is very important. It's a key factor. So knowing the material, then you have to think how best can you produce the material, to have a high quality and with a close tolerances, because the brake disc has several tolerances which is very tight, and this has to be you should be able to meet it and produce it. So these are another hurdles that need to be crossed. Next is acceptability by the stakeholders. So you know that from ages, gray cast iron material are being used for the manufacturing of a brake disc. Then if you are changing the material, it must be acceptable by the stakeholders. And for that to be done, then it means all the tests I've mentioned above here must be passed or fulfilled, because that is the only way you could convince the authorities, the governmental authorities or the OEM that we use the part in their vehicle, to accept it. So this is another important challenging area. Next is brake disc development requires a joint effort from the automakers. So here, because if you are not producing complete vehicle, then you need a joint collaboration with the automakers, to design and develop an acceptable brake rotor from the new material. So this is another challenge. So needs to be crossed. Besides all the above mentioned, so it is a capital intensive venture. So all that I've mentioned, all the tests I've mentioned here before, requires a lot of money, to perform all those tests. They are not cheap; they are very expensive. So a lot of money is needed to do that. And lastly, it is a time-demanding process. So different, all these tests need to be done at different stages. So which is a time-demanding process or procedure. Next, we look at some of the basic tests that need to be passed or fulfilled by the new rotor developed. So one of it is a hairpin descent. So where is done via dyno, and also could be also performed through vehicle testing. So where the car is being driven at a 20 km per hour, is constant. Then with energy input with a long time, approximately 20 minutes, so downhill. So this has to be passed. So because here you see how the friction behave, and the heat, how it's generated and dissipated. So several other factors you analyze. Then another one is a very tough testing procedure. We call it AMS 100 test procedure, or field test. And here you drive the vehicle at very high speed, 100 km per hour, for a short seconds, 2 seconds. You have to apply brake. So bring the car to 0 km per hour, and at the same time, you accelerate it to 100 km per hour, bring it down. So you have to do it 10 times. And during this 10 times braking regime, what happens is that you accumulate a lot of heat on the surface of the disc over, less than 2 minute brake regimes. So you accumulate a lot of heat. And the essence is that to see if the brake material will lose its friction property. So that is what we call fade test. So, and as a result, there will be increase in temperature on the surface of the rotor, so which could lead to fading of the friction. This has to be passed. Then next is a single stop. This is a non-transient. So sorry for the mistake. It's not. It's a non-transient energy input. So which you apply from maximum speed, to 0. So in less than 10 seconds application. So this has to be passed as well. And the fourth one I put here is a high load crack test. This is subjected to extreme load case. This, we want to see how the material will fail if a crack will be developed on the surface. So this is, and for gray cast iron, when you are under this condition, there will be phase transformation in the microstructure, which will also influence the response of the disc during braking. So this will be analyzed, and how crack is developed. Then another thing that also analyzed during this is a deflection of the disc or coning of the disc. Because if that happens, then that could lead to noise issue, because there will be variation in the thickness of the disc. So this must be passed. So And there are other test procedures that need to be passed, but here I limit to these 4. So, and it is when all these test procedures are passed, then you could have something to present to the authority or to the OEM to convince them to accepting the rotor you have developed from new material. Yes. Here, I will talk briefly. So I will talk briefly on the. Oh, sorry, what happened? Sorry, that was a little mistake. Yeah. So I will talk briefly on the journey of a Sika-like development procedure or process. Aluminium rotor that was developed at the AC Fluby started in 1995 when the concept was started, and the brake rotor design started during this period. And later on in 1998, so discussion about how this could be manufactured was started. The process of manufacturing the rotor and the material. So all those was started in 1998. And in late, 1999 to 2000, so patent application was filed for the rotor development and the surface treatment. So this was filed, and later on in 2023, unfortunately, the manufacturing process was disassembled because of lack of interest from the OEMs, that is original equipment manufacturer, which means automakers. So because at that point, no interest, so and no vehicle program whereby Sika disc could be employed. So that creates some kind of setback at that point in time. But later on, in 2010, 2011, so the interest came back from OEM. So, and the installation of the equipment started, and more validation testing were conducted to convince the OEM. So that started, and between 2011 to 2013, so we have the first customer, and the production of a prototype were made. And during this period, we produced several discs. So for different vehicle as a rear disc. For example, like the Volvo V40 was equipped with this Sika disc, that is rear disc. During this period, about 25,000 of the rotor were produced and used during this period. But continue 2016 to 2017, there was discontinuation of using the rotor because of the cost. Because at that time, the cost of producing the aluminum rotor was higher compared to the traditional rotor, even though with a good benefit of using it, but due to the cost. So this creates some kind of lack of interest from the OEM. And at the same time, there was lack of motivation to continue using the rotor because there is no regulation or legislation that said that this rotor should be used. So that creates some kind of a little setback. But interestingly, in 2018 up to now, there is interest from different OEM due to the new legislation, especially non-exhaust particle emission. and also the advent of electric vehicle, where you need to reduce the weight and you need to solve the corrosion issue. So these aluminum rotor become very important and fit into those programs. So there are several interests, and this further development on the rotor was conducted, and a new opportunity were opened. So from different OEM. The major trend in the automotive industry, yeah, we talk about three major trends, and the first is the electrification of the vehicles. So this now is statistics shows that increase in vehicle electrification in the auto market will continue to dominate and increase. So, and this comes with some other challenges, which I will discuss in the next page. And next is a non-exhaust particle emission. So this is become more focused. Right now, last year, there was information of Euro 7 regulation on particle emission. So the exhaust emission have been well controlled. Now that we have electric vehicle, so non-exhaust emission become important part to control. And the other part is circular economy, which is another important area in the automotive industry. So dealing with sustainability, dealing with recovery and recycling of material. These are some big area that is trending in the automotive industry currently. Now, a little dive into the difference between the traditional traditional vehicles and electric vehicle. Here, in relation to braking system. In the traditional vehicle, the brake rotor are used 100%. So friction brake is used 100%, and that means brake cast iron is good enough. Corrosion issue will not be a big problem for the traditional vehicles, because pad always clean the friction plane or surfaces of the disc. But for the electric vehicle, so most of the braking are done on regenerative braking. 90% of it is done on the regenerative braking. And although the vehicle is still equipped with a frictional brake system, but these frictional brake systems are seldomly used. So approximately like 10%. These are needed mainly in case of emergency braking. So, and in that sense, what will be the problem is that when the frictional brake system is not frequently used, then the issue of corrosion will be prominent. So here is the major challenges of electrification of vehicle in relation to brake rotor. One is the increase in the vehicle weight. So, and this we see because the battery in electric vehicle constitute approximately 25% of the vehicle weight, which is very huge. And it is good if we could equip that vehicle with a lightweight rotor. In that sense, it will reduce the rotational inertia when using the rotor. And as a result of that, it will improve the acceleration of the vehicle. So it is another one is, as I've mentioned earlier, if traditional brake disc is used in an electric vehicle, corrosion will be a major challenge, as you can see in the image. And if this rust continue on the friction surface of the disc over time, then it will lead to pitting on the surface of the disc. And when that happens, then there will be vibration issue that will lead us to NVH issue, which is a noise, vibration, and harshness. So this will happen, and Joda problem will occur during braking. So this will be a big challenge. And as a result of that, when rust is developed, then more particles will be generated, which lead to non-exhaust particle emission. So this will be some of the major challenges related to brake system of electric vehicles. Now, next generation brake rotor, a case study of a Sikhalite disc. Here, why Sikhalite disc could be the next generation brake disc. One, it is lighter in weight, which means weight reduction, approximately more than a 5 kilogram weight per car is saved if aluminum rotor is used. And also, using this for electric vehicle, you reduce rotating armstrong mass, and that implies that you improve the acceleration of the car. The next is that non-exhaust emission reduction. So we've seen that the aluminum rotor have excellent wear resistance, which means it doesn't wear. And low non-exhaust emission is achieved, and which is mainly come from the brake pad. The aluminum rotor, that is Sikhalite rotor, doesn't wear on itself. Then, issue of corrosion is a thing of the past for Sikhalite disc. No disc thickness variation, no NVH issue, no dust on the rim, which means it's also it will reduce warranty cost. So, because when the owner of the car doesn't have any issue with the brake system, then there's no need of contacting the manufacturer for claim. Then we also see that improved end customer experience. So it is durable for the whole life of the vehicle. It reduces cost of ownership. So no need of changing the disc during the vehicle lifetime. And finally, so in this webinar, we've talked about the purpose of the automotive brake disc and the factor influencing its performance. And next, we look into the essential properties of a brake disc material. And briefly, we talk about some challenges of changing brake disc material. Basic standard brake disc performance tests that need to be met. And the trend, the major trend in the automotive industry, and the challenges of vehicle electrification. And finally, we talk briefly on the developmental process journey and the basic characteristics of a Sikhalite disc as a brake disc material for the next generation brake disc. So, thank you.
Thank you very much, Samuel. Very interesting. So please keep all your questions for the discussion later. Write them down so you don't forget them. And after Samuel, we will let Lucia on stage. Please, the floor is yours.
Thank you very much, Madeleine. While I share my screen, then I take this time to briefly introduce myself. I'm a postdoc here at Jönköping University, and my research projects are all about aluminum-based composites. So, and in collaboration with several companies, and AC Fluby is one of them in all of the projects. So as Samuel presented, we saw together that standards and regulation are now evolving with new sustainability demands. So aluminium-based composites can be a valid candidate material to substitute gray cast iron. The main features are that you can get 50% lighter disc, better corrosion and wear resistance, and 3 times greater heat conductivity. But there are also other aspects that can be developed even further and that we are looking into with our research project. For example, one challenge is to improve the maximum operating temperature of the material. Also, another aspect to look into is the evaluation of the end of life of this product or the composite in general, and the sustainability role that this material has then at the end of the life of the product. So as Samuel said, now there is a new interest in this kind of material, although they were originally developed in the 90s. And as you can see, this new interest is both from the academic community, as you can see from the article side. If you look for aluminum silicon carbide metal matrix composite, there has been a peak in publication in the recent years. And this is mirrored also in the number of patents that has been approved in the recent years, again, with a huge peak compared to when these kind of materials were initially developed. So this new interest is not only from the manufacturer side, but also from a research point of view. So let me show you what are we doing here at the university and what active projects we have for this material. The first one is called Proforal and is about properties and formability of aluminum-based composites. It's in collaboration with the Gränges, Husqvarna, Comtech, and of course AC Flubi for the brake disc. And in this project, we look into several strategies to improve the maximum operating temperature of the aluminum composite. The other project is called Mareal and is about manufacturing of aluminum composite brake discs from recycled alloys. So to take one step further towards sustainability and see how recycled alloys affect the properties of our material. This is also in collaboration with Gränges, Comtech, the Swedish Research Institutes, and AC Flubi again. So looking into Proforal, the strategy was to optimize the matrix for high temperature. That was our first step. And then we evaluated different mechanical properties, but also the durability as wear and hardness. And also we looked into corrosion a little bit and thermophysical properties for the heat conduction. Then the second step is to look at the process optimization to try to reduce cycle time. The brake discs are currently produced with squeeze casting, which is an excellent technique, but we wanted to see if high pressure die casting combined with warm forming could let us gain a little bit of time in the cycle production. And then at the end, we looked at the components of interest. In this case is clutch drum for the Husqvarna side and brake disc for the AC Flubi side to really see if this material is really promising in this case. So we started with changing the matrix alloy, and we decided to look into different possibilities of alloying elements to improve the mechanical performance at elevated temperature. So the first choice was nickel, because it's known to form reinforcing phases that are thermally stable in aluminum silicon alloys. And thinking of sustainability, nickel is not on the critical raw material list. Then we looked at, we decided to also add copper because it is also known to interact with nickel in reinforcing precipitates during thermal exposure. Is not on the critical raw material list, but the challenge with copper is that has issues with the corrosion and ecotoxicity. So if it is dispersed in the environment, there are some regulations that limit its use. But to keep all our possibilities open, we decided to also go for that. And then we also decided to try to look at the role of lanthanum and cerium, so rare earth elements in this case, which in literature are said to have has-cast matrix strengthening, but they are also, the negative side is that they are on the critical raw material list. So that would be a challenge for sourcing in this case of these two elements. But how does a composite really look like when we look at the material in the microscope? If you're not familiar with it, let me just briefly explain to you. We have our matrix, which in our case is an aluminum silicon matrix. So here you see the aluminum dendrites and the aluminum athetic. The matrix alloy is an aluminum 9 silicon in the CK material that AC Flubi developed. So is the bright part in these images. The dark polygonal particles are instead our carbides, so the reinforcement that is added to the matrix to build the composite itself. And then we can have additional intermetallic phases when adding alloying elements, as we said. So for example, we can have intermetallics formed with nickel, still in the interdendritic space, or with lanthanum and cerium combined together. And all these phases contribute in a different way to the strengthening of the material. If we look at the mechanical properties, we were very satisfied with the different results that we could see. So nickel really gave a significant improvement of the mechanical properties at room and elevated temperature up to 470 degrees. The copper addition after nickel kept that improvement constant, but without additional effect of reinforcement. Lanthanum and cerium instead showed a promising improvement even when combined with both copper and nickel. So these results are very promising from the mechanical point of view, but then we also took care of, as I said, of wear and thermophysical properties to be sure that we weren't sacrificing those aspects because they are still critical properties for the brake disc application, as Samuel presented. So the next step of the project is to, after that, I said, is to explore the possibilities in terms of process optimization in the effort to reduce cycle time for this kind of material. And then at the end, we will also move to component validation because all the tests that we do are at the laboratory scale, but we also want the real point of view with the real component in the end to be sure that all the steps that we take are satisfying for our partners. Moving to Mareal, as I mentioned earlier, in this project, we focus more on the sustainability aspect of these materials. So the aim is to add different amounts of recycled alloy as the matrix for our metal matrix composite. We check the microstructure and the mechanical properties mainly to be sure that this material still satisfies all the requirements to validate the performance in a lightweight brake disc that is also sustainable. And then another question in our project is to start to look into the recyclability of the composite itself. So what happens when at the end of the life of the brake disc, when the material comes back, when we remelt it, how do the carbides behave? We know that there is a settling effect. So how to does it make sense to separate the carbides from the matrix and recover the two materials separately, or we can still steer again the carbides and give a new life to the material? We directly noticed trying using 100% of recycled matrix alloy that the recycled metal greatly affects the distribution of the carbides in the microstructures, as you can see in this picture for comparison. So what we are looking into more is, does the difference in dispersion changes the properties, but does it change it in a too damaging way, or we can still make compromises and accept these new properties? So how much are we affecting the properties of our material for the final application of the brake disc in mind? So we will look into we will compare the role of different fractions of recycled alloy in the matrix, and then we will look again into mechanical properties, thermophysical and durability behavior of this material at a laboratory scale to start with, and then we will move to component validation to see the influence on a larger scale for this kind of application. So to summarize, we look at the aluminum-based composites from different points of view, trying to improve the maximum operating temperature. What are the possibilities there? How much we can play with the matrix alloy and with the process. And then also looking into the sustainability potential of these materials, or let's say of the composite brake disc themselves. Thank you very much.